Okay, so we have, as we've been discussing, we showed this control loop in fact, it's a flow control loop because flow is what this one is controlling. But let's take a little closer look at the flow controller itself. All right, now this is a schematic. This is a schematic of the controller. So we talked about we had process feedback in the case of the flow controller. What we were measuring and sending back as feedback was the rate of flow in the pipe by using this differential pressure device. So the DP, the differential pressure device, is sitting here. It probably incorporates the transmitter to convert the signal to 4 to 20 milliamps, coming back to this junction right here. The set point is the knob that we had right here, with which we could manual, or just by taking our hand, go up and change it to whatever rate of flow we wanted to have. 10 gallons a minute, 100 gallons a minute, 1,000 gallons a minute, what have you. Okay. And then we had the output amplifier from the controller. Okay, the output amplifier sends a signal out and back to the controlling device, which is a control valve for what we're looking at. So this is the manipulated variable. Okay, so that's what it looks like in schematic form. Now then, let's take a look at what takes place right here with this Greek letter S for summation. Okay, I look at my feedback. You notice I bring it to a negative junction, and I have the set point, which goes to a positive junction going into the summing point. So I actually subtract my process feedback from my set point, and if that does not equal 0, that means I have an error. Okay, if the set point minus the feedback is not equal to 0, I have an error. I have an error between the rate of flow in my pipeline and my set point. Now then, this controller, I'm going to say at this point, is a PID controller, which means we do a multiplication, we do a mathematical integration. The I stands for integration, P stands for proportion, and D stands for derivative or differential. And what we'll do is we'll ignore the D for right now, because we're not working with a system that really requires that math function. So if I have an error, I multiply my error, there it is, the E with a T in the parentheses, by whatever number K I have set at. Okay, so I can set K at a big number, or I can set K to 0. Okay, same thing for the integration right here. I have a multiplier, and I can set K for a big number. I can set K for 0. If I set K for 0, then it just shuts those two math functions down. Nothing happens. But if I've got an error, my proportional amplifier multiplies the error by the number K, sends it through this summing junction to the output amplifier, and the output amplifier is the one that will send, and let's just say it will send a 4 to 20 milliamp signal to the actuator. For our flow control loop, the actuator is sitting on top of this valve and will operate the valve. The error is a neat thing. Okay, if I have a difference between my process feedback and my set point, okay, the integrator will start to change. And as long as that error stays there, as long as that error is not zero, it will continue to change. The output from this module right here, going to the output, will begin to climb, and it will continue to climb, and it will continue to climb, okay, until the error is pushed back to zero, because that's what we're trying to do, right? We would like for the process feedback and the set point to be the same for the duration of this controller, okay? Let's see if we can talk about that just a little bit more. And I'm going to get rid of my picture here. I know that breaks a lot of hearts. I've been offered a lot of money for this artwork that I do. Just kidding. So let's draw a graph, a couple of graphs maybe. Here's my y-axis, here is my x-axis, or t for time. Actually, it is time. Okay, and what we will do is we will say this graph right here is going to be the error. Okay, with this being 0. And this is going to be the output of the integral. I'll say integral output. So let's say our process is operating and we don't have an error. The set point is equal to the process feedback, so it's happy. Okay, the integral just happened to be at 0. Okay, and I'll just draw it like that because the error was at 0. And then all of a sudden we get an error. Okay, what will happen is the integral will start to change. It will keep on climbing, and will keep climbing, and will keep climbing. Okay, and it will be pushing the valve, either close or open, whatever it has to do. Okay, until this error, okay, drops back to 0, and then the integral will stop changing. Okay, you know, and I will, let's say my error goes the other way. Okay, now then my integral will start coming down this way, slowly changing the valve, okay, until it pushes the error back. Now then, this is not exact, okay, and it's not meant to be exact. It's just to talk about the integral and for you to know that integration takes place in a ramping form, climbing or declining. Okay, it can go negative, but as long as the error is there, the output of the integrator in the PID controller, okay, will continue changing. Okay, as long as the error is there. Okay, once the error drops back to 0, the integral will stop changing, and it will sit at its last value until something else happens. But we will talk about this a little bit more. Perhaps we can do something with our lab equipment tomorrow to take a look at what this is about. But if you do not have one of these diagrams, please get one, because we will be having an exam with that. Okay, see you tomorrow.